In our first numerical example with our full suite of equilibrium equations, we're going to find the force in the link at A and the reactions at C. So in the setup of this, let's go back and review a couple of things. Our statement of equilibrium is as follows. And this can be done in a variety of ways, but one way is sum of all the forces in the x direction are going to be 0. Sum of all of them in the y direction are 0, and the sum of moments about any one particular point would be equal to 0. Now another way we could express this is one independent set, is sum of forces in the x equal to 0, sum of moments about one point would be 0, and sum of moments about another point would be equal to 0. That is one way to do it. And then finally we could do it as the sum of moments about a point is 0, sum of moments about another point is 0, and a sum of moments about a third point are 0. We choose which approach to do with whatever is going to get us there the shortest, quickest way possible. Right, so that's a key critical thing. There's our equations of equilibrium that we have to work with. Right, now the other thing to look for is note that we have a link support. Now how do you identify them? We have a pin connected member, okay, so notice AD is pinned on either end. Now ACB is also pinned, so wait a minute, is that a link? No, it's not. It's going to be a beam. So the pin connected member and no loads applied. And I should probably go back and say we only have two pins in that pin connected member, A and D. Right? Whereas here with member ACB we have a beam, we've got some forces associated with the pin support at C, we've got something happening because of the link, and we have an applied force out there. So we have at least 3 forces applied to member ACB. Alright, now one more thing here. So what's the consequence of a link? It says that it is like a cable, but only like a cable. A link can also be in compression. A cable can only be in tension, but we relax that for a link. It can be in tension or compression, but only that. Nothing else. No bending is going on. And we will, in the next lesson, talk about or derive why that might actually be the case. Alright, so let's go back then. Determine the force in the link at A and the reactions at C. So what we're going to do is to come along and say, hey, let's do the free body diagram. That's our basic tool that we use in statics, and we're going to do it of this beam ACD, and then start to see what happens. All right, so let's get the body in first, and it's at this 20-degree angle. There we go. And now here's the key on free body diagrams. You have got to show what you removed from the body and its effect, not what happened to it. So what I mean by that is, if just think about this from a simplistic viewpoint. If we put the pin here at C and we put this 75-pound force on there, it's going to want to try to spin this in a clockwise fashion. What's preventing it is AD from doing that, and AD would want to try to stretch out. So that means, of course, that it's going to go into tension. Right? And that will be the force. We'll call it, it's tension. I'm just going to call it the tension here. Right? And then at C itself, we have a pin. So we have two unknowns. We have the vertical component. And now you can tell, because there's a horizontal component in the tension of the cable, that CX is going to have to go the other direction in order for the to be equilibrium. So we can kind of guess what's going to happen before we even go too far with this. Right? So note, we're not trying to draw the tension in the cable, we're trying to draw the effect of the link on the body that remains. Right? That's a crucial, subtle distinction that matters actually quite a lot in reality. Right? So primary tools in statics are free body diagram, and then what the heck do we do with it? Well, we apply our equations of equilibrium. And there's a lot of clever things we might do to get to where we want, which is to find the force in the link at A and the reactions, Cx and Cy, and we get those 3, we're done. Notice 3 independent equations, 1, 2, 3 unknowns. Whoa, I like that. That means that we can solve for our unknowns. Right, so I could use sum of forces in the x, but notice if I do that right off the bat, I'm going to have cx and the x component of t in there. So that doesn't sound very useful to me. We could, wait a minute here, because if we do cy, I'm going to also have the ty in there. But look what happens. If we were to some moments about point D, right, we don't have to do this on the body. If we do some moments about point D, cy and t go away, and there's going to be even a more profound or even better result if we do this. So let's check it out what happens. Some moments about point D, and if we take counterclockwise positive, why? Because cx is going around in a counterclockwise fashion about point D, so that's what I'm going to choose to do. Notice my moment arm is given to me directly. I don't have to go determine it. It is exactly right there. I like that. That makes life a little bit easier. Less likely I'll make a mistake. So 12 inches times cx, b plus, I don't have to have t and cy because they're out of it. And then I got 75 pounds going the other direction. And I got to find then its perpendicular distance. Right? So I need to find this distance right here. And it's not given to us, so we can find it though. Draw it out here, draw it out here. I'm getting a little sloppy trying to rush through this. Oh, it's a part of this right triangle. That's right there. So that's 15 inches times cosine of 20 degrees. Set it equal to 0 for equilibrium. And let's see what we get for cx. We're going to have, alright, 75 times 15 times 20 cosine equals, divide by 12 equals 88.1, actually 096. Yeah, it's equals 88. Temporarily, I'm going to leave a ridiculous number of significant digits here. I'm going to come back and clean that up in a second. The positive means that it's acting in the direction shown, not that it acts to the right. It means I've got it showing acting to the left. I did the math assuming it acted to the left, and I guessed correctly. So that's the x value. Alright, so how could we go find out the y value here? Now, we could be clever and do the same kind of thing with cx and t. We could find out some new point where they intersect. I don't have any distances there. And nothing easy, I think, to calculate, so I don't really want to do that. I'm not too interested in that one. Alright, so what if we were to some moments... See, I'd really like not to use cx, because what if we made a mistake? I'm not seeing any... Well, you know, we could just some moments about point C. Hey, let's do that. Let's some moments about point C. We'll get rid of both cx and cy. I'm going to take positive clockwise or counterclockwise again, and we'll have minus 75 pounds times 15 inches times cosine 20 degrees again. But instead of taking t at A and breaking it into components that are towards C and all that kind of business, what if we just take it down here? Because if we do that, then I only need the tx component. I like that a lot. Now, I do have to figure out what the heck the angle is, and I'm not sure that we have information. Let's see, the beam is at 20 degrees, but I don't have any other information here. So let's do the triangle real quick. Maybe it's going to be law of sines or law of cosines that we're going to fuss with to get this. We know that that's 12 inches. We know that that's 10 inches. We know that that's 20 degrees. So that makes that 70 degrees. But I don't know this angle, and I don't know the whole angle here. Huh, well that stinks. Alright, so I think what we're going to have to do, let's see, I could do law of cosines, couldn't I? Ooh, yeah. Yeah. What do you mean, yeah. It doesn't, that'd give me this thing, but so what? What if, yeah, I don't like anything, to be honest, but if we do this, now we got a right triangle, we can find this height, and that's going to be 10 times 20 sine, 3.42 inches, and minus 12 means this down here is 8.58 inches. So, okay, how does that help me? Well, I still need this in order to find any one of these angles, or I have to get that hypotenuse again. I'm kind of stuck here, and I'm going to have to get that somehow. And so 10 times 20 cosine would be this 9.3969, square it, plus the 8.58, square it, radical. So that's 12.72, and that divided by 12 is, I didn't have to do it this way, but I ended up doing it that way. So inverse tangent would give me 43.3 degrees. Right, that's inverse tangent of 12 over 12.72. Okay, all of that. Alright, so now that's with respect to the vertical. So I want the horizontal component of t. There's your 43.3 degrees. So we're going to have a moment arm of 12 inches, and then t times, then let's see, again, vertical component, I want the horizontal, so 43 is here, that would be opposite. So sine of 43.3 degrees, set it equal to 0. Not really good paper management here. Sine times 12 equals, take the reciprocal, times 75 times 15 times 20 cosine, and we get that t equals 128.4. Wow. So that's pretty big, right? It should be big, right? Because look, we got 75 pounds times a moment arm that, you know, it's not really 15 inches. It's 15 times cosine of 20, which is pretty close. And this is shorter distance, right? So this has got a smaller moment arm. It's going to get bigger. So that actually makes a lot of sense that t would end up being like that, right? And then we finally have to get cy. All right, well, let's see. What would be a clever way to get cy? I can't get rid of cx and t unless I go out here. I don't want to do that. And I don't like using other results, but it looks like that's what we're going to do. Sum of forces in the y will take upwards positive. We'll have cy minus 75 minus the y component of t, which is 128.4 times cosine of 43.3 degrees. And then we're going to have that cy equals 168.4 pounds. Right, so what's our final answer here? Cx is equal to 88.1 pounds acting to the left. Cy equals 168.4 pounds acting up. And T is in tension, 128.4 pounds. And that's the force in the link. And there's our 3 answers that were requested.